Beyond the cosmic horizon, humanity's journey through the infinite expanse. Since the dawn of consciousness, humanity has gazed upward at the night sky with wonder and curiosity. Those ancient observers who first tracked celestial movements could scarcely have imagined that their descendants would one day walk on the moon, send robotic explorers to distant worlds, and capture images of galaxies born billions of years ago. The story of space exploration represents not merely a technological triumph, but a fundamental expansion of human perspective, a journey that continues to redefine our understanding of existence itself. The cosmic ocean, our solar system. Our journey through space begins at home, within the relatively small neighborhood of our solar system. This cosmic backyard, dominated by our G-type main sequence star, the Sun, contains 8 diverse worlds, over 200 moons, millions of asteroids, and countless comets and Kuiper Belt objects. Yet this entire system spans merely 287 billion kilometers in diameter, a vast but infinitesimally small region when compared to the scale of our galaxy. The inner solar system presents 4 terrestrial worlds: Mercury, Venus, Earth, and Mars. Mercury, closest to the Sun, endures temperature extremes from 173 degrees C to 427 degrees C, with virtually no atmosphere to retain heat. Its cratered surface tells a story of billions of years of bombardment by space debris. Venus, often called Earth's twin due to similar size, represents a cautionary tale of planetary evolution. With surface temperatures around 462 degrees, hotter than Mercury despite being farther from the Sun, Venus demonstrates the devastating effects of a runaway greenhouse effect. Its thick atmosphere, composed primarily of carbon dioxide with clouds of sulfuric acid. Earth stands alone in our solar system as the world known to harbor life. Its unique position within the habitable zone, where liquid water can exist on the surface, combined with a protective magnetic field and appropriate atmospheric composition, created the conditions necessary for life to emerge and evolve. The Moon, Earth's only natural satellite, plays a crucial role in stabilizing our planet's axial tilt, thereby maintaining relatively stable climate conditions over geological timescales. Mars, the 4th terrestrial planet, has captivated human imagination for centuries. Once believed to be home to an advanced civilization, we now understand it as a world that may have had conditions suitable for life in the distant past. Evidence suggests that Mars once had flowing water and a thicker atmosphere. Today, it's a cold, arid world with a thin atmosphere composed mostly of carbon dioxide. However, beneath its surface, Mars may still contain liquid water reservoirs, making it a prime target in the search for extraterrestrial life. Beyond the asteroid belt lie the gas giants, Jupiter and Saturn. Jupiter, the largest planet in our solar system, contains more than twice the mass of all other planets combined. Its great red spot, a storm larger than Earth, has raged for centuries. Jupiter's extensive system of 79 known moons includes the 4 Galilean moons, Io, Europa, Ganymede, and Callisto, each with unique characteristics. Europa, in particular, has attracted scientific interest due to the possibility of a subsurface ocean containing more water than all of Earth's oceans combined. Saturn, renowned for its spectacular ring system, consists mainly of hydrogen and helium. Its rings, composed primarily of ice particles with a smaller amount of rocky debris, extend up to 282,000 kilometers from the planet, yet are remarkably thin, with a vertical thickness of only about 10 meters in most places. Saturn's moon Titan possesses a thick atmosphere and liquid hydrocarbon lakes and rivers, making it one of the most Earth-like worlds in terms of surface processes, albeit with methane rather than water. The outer solar system is home to the ice giants Uranus and Neptune. These worlds contain more ices, such as water, ammonia, and methane, along with rocky material and hydrogen and helium. Uranus rotates on its side with an axial tilt of 97.77 degrees, possibly due to a cataclysmic collision in the distant past. Neptune, the farthest known planet from the Sun, has the strongest winds in the solar system, reaching speeds of up to 2,100 kilometers per hour. Beyond Neptune lies the Kuiper Belt, a circumstellar disk of icy bodies, including the dwarf planet Pluto. This region, along with the scattered disk and the hypothetical Oort cloud, represents the outer edges of our solar system and contains remnants from the solar system's formation 4.6 billion years ago. The stellar neighborhood, our galaxy, and beyond. Our solar system resides in the Milky Way, a barred spiral galaxy approximately 100,000 light-years across. Containing between 200 and 400 billion stars, the Milky Way is just one of billions of galaxies in the observable universe. Our Sun orbits the galactic center at a distance of about 26,000 light-years, completing one revolution approximately every 225 to 250 million years in what's known as a galactic year. At the center of our galaxy lies Sagittarius A, a supermassive black hole with a mass equivalent to about 4 million suns. Black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape, represent some of the most extreme environments in the universe. They form when massive stars collapse under their own gravity at the end of their life cycles, or through other processes in the early universe. The Milky Way belongs to the Local Group, a collection of more than 54 galaxies, including the Andromeda Galaxy, the Triangulum Galaxy, and numerous dwarf galaxies. The Local Group itself is part of the Virgo supercluster, a massive structure containing at least 100 galaxy groups and clusters. The universe's large-scale structure resembles a cosmic web, with galaxies and galaxy clusters forming filaments and sheets surrounding vast voids. This structure emerged from tiny density fluctuations in the early universe, amplified by gravity over billions of years, the expanding universe and cosmic origins. In 1929, astronomer Edwin Hubble made a groundbreaking discovery that would revolutionize our understanding of the cosmos. Galaxies are moving away from us, and the farther away a galaxy is, the faster it recedes. This observation, now known as Hubble's law, provided evidence that the universe is expanding. The expansion of the universe implies that it had a beginning, a moment when all matter and energy were concentrated in an extremely hot, dense state. This realization led to the development of the Big Bang theory, which describes the universe's origin and evolution. According to this theory, approximately 13.8 billion years ago, the universe began expanding from an initial singularity, undergoing rapid inflation in the first fraction of a second. As the universe expanded and cooled, fundamental forces separated and elementary particles formed. Within the first few minutes, protons and neutrons combined to form atomic nuclei, primarily hydrogen and helium. It took about 380,000 years for the universe to cool sufficiently for electrons to combine with nuclei, forming neutral atoms and allowing light to travel freely for the first time. This first light can still be detected today as the cosmic microwave background radiation, a faint glow of radiation that permeates the entire universe and provides a snapshot of the infant cosmos. The formation of the first stars and galaxies marked the beginning of the cosmic dawn. These early stars, composed primarily of hydrogen and helium, forged heavier elements through nuclear fusion. When these stars reached the end of their lives and exploded as supernovae, they enriched the cosmos with these heavier elements, which would eventually become incorporated into new stars, planets, and life itself. The search for extraterrestrial life. One of the most profound questions in science is whether life exists beyond Earth. The discovery of extremophiles, organisms that thrive in conditions once thought inhospitable to life, has dramatically expanded our understanding of where life might exist. From deep-sea hydrothermal vents to acidic hot springs, from Antarctic ice to nuclear reactors, life has demonstrated remarkable adaptability. In our search for extraterrestrial life, scientists focus on worlds with conditions that might support life as we know it. The habitable zone concept identifies regions around stars where liquid water could exist on a planet's surface. However, this definition may be too restrictive, as moons with subsurface oceans like Europa or Enceladus might harbor life despite existing outside the traditional habitable zone. The discovery of thousands of exoplanets, planets orbiting stars other than our Sun, has revealed that planetary systems are common in our galaxy. Among these exoplanets, some reside in their star's habitable zone and possess sizes and densities similar to Earth. The TRAPPIST-1 system, located about 40 light-years away, contains 7 Earth-sized planets, 3 of which orbit within the habitable zone. The search for intelligent life continues through projects like the Search for Extraterrestrial Intelligence, SETI, which monitors the cosmos for signals of technological origin. Despite decades of searching, no definitive evidence of extraterrestrial intelligence has been found. The Fermi paradox highlights this contradiction between the high probability of extraterrestrial civilizations and the lack of contact with such civilizations. The future of space exploration. Humanity's journey into space has entered a new era, marked by increasing international collaboration, the emergence of private space companies, and ambitious plans for lunar bases, Mars exploration, and beyond. The International Space Station, ISS, has served as a platform for continuous human presence in low Earth orbit for over 2 decades, facilitating scientific research and technological development. Future plans include the Lunar Gateway, a planned space station in lunar orbit that will serve as a staging point for lunar surface missions and eventually Mars expeditions. Robotic exploration continues to push the boundaries of our knowledge. Missions like the James Webb Space Telescope, launched in 2021, are revolutionizing our understanding of the early universe, exoplanet atmospheres, and the formation of stars and galaxies. Meanwhile, rovers on Mars, orbiters around Jupiter and Saturn, and missions to asteroids and comets continue to provide unprecedented insights into our solar system. The prospect of human missions to Mars presents numerous challenges, including the long-duration spaceflight effects on the human body, the psychological challenges of isolation, and the technological requirements for sustaining human life on another planet. Despite these obstacles, plans for Mars exploration continue to advance, with some space agencies targeting the 2030s for the first human missions. Looking further into the future, concepts like interstellar probes, space-based solar power, asteroid mining, and terraforming represent potential frontiers in humanity's expansion into space. While some of these concepts remain speculative, they illustrate the ambitious vision driving space exploration. Conclusion: the endless frontier. As we contemplate the vastness of space and our place within it, we are reminded of how much we have learned and how much remains to be discovered. Each answer we uncover reveals new questions. Each horizon we cross exposes new frontiers. The universe continues to surprise us with phenomena that challenge our understanding, from dark matter and dark energy to the possibility of multiple universes. Space exploration represents more than a scientific endeavor. It reflects a fundamental human drive to explore, to understand, and to transcend limitations. In seeking to comprehend the cosmos, we ultimately seek to understand ourselves, our origins, our future, and our significance in the grand scheme of existence. As we stand at the threshold of a new era in space exploration, with technologies and capabilities that previous generations could only dream of, we carry forward the legacy of all those who looked up at the stars and wondered. The journey has just begun, and the greatest discoveries may still lie ahead, waiting in the infinite expanse beyond our cosmic horizon. The cosmic ocean, our solar system. Our solar system, a mere speck in the Milky Way, spans 287 billion kilometers and hosts an astonishing diversity of worlds. Beyond the asteroid belt, the gas giants Jupiter and Saturn dominate the outer realms. Jupiter, a colossal sphere of hydrogen and helium, exerts such gravitational influence that it shields Earth from countless comets and asteroids. Its great red spot, a storm larger than Earth, has raged for over 350 years, with winds reaching 640 km/h. Jupiter's 79 moons include the Galilean quartet, Io, racked by sulfur volcanoes; Europa, with a subsurface ocean holding twice Earth's water; Ganymede, the solar system's largest moon; and Callisto, a cratered relic of the early solar system. Saturn, though less massive, captivates with its ethereal rings. Composed of 99.9% water ice, these rings span 282,000 kilometers, yet average just 10 meters thick. Saturn's moon Titan boasts a thick nitrogen atmosphere and liquid methane rivers, while Enceladus spews icy geysers from its subsurface ocean, hinting at hydrothermal vents, potential cradles for life. Farther out, Uranus and Neptune, the ice giants, reveal mysteries. Uranus rotates at a 98-degree tilt, likely due to an ancient collision. Its blue-green hue comes from methane-absorbing red light. Neptune, the windiest planet, hosts jets reaching 2,100 km/h. Its moon Triton orbits backward, suggesting it was a dwarf planet captured from the Kuiper Belt. The Kuiper Belt itself, a ring of icy bodies beyond Neptune, is home to Pluto, Eris, and Makemake. Pluto's heart-shaped glacier, Tombaugh Regio, is made of frozen nitrogen, while its mountains tower 3,500 meters. Evidence of geological activity. Beyond lies the scattered disk and the Oort cloud, a hypothetical reservoir of comets extending nearly 1 light-year from the Sun. Each world tells a story: Jupiter's violent storms, Saturn's delicate rings, Neptune's supersonic winds. Yet for all their grandeur, these planets are but stepping stones. As Voyager 1's pale blue dot image reminds us, our entire solar system is infinitesimal against the cosmic stage, a truth that propels humanity toward the stars. The stellar neighborhood, our galaxy and beyond. Our Sun orbits the Milky Way's center at 220 km/h, completing one revolution every 230 million years. This barred spiral galaxy, 100,000 light-years wide, contains 400 billion stars. At its heart lies Sagittarius A, a supermassive black hole 4 million times heavier than the Sun. Its event horizon, the point of no return, spans 24 million kilometers, yet it appears minuscule from Earth, 26,000 light-years away. Black holes form when massive stars collapse. Their gravity warps space-time, causing time to slow near their edges. Stellar mass black holes, like Cygnus X1, pull matter from companion stars, creating X-ray flares. Supermassive ones, like Sagittarius A, grow by merging with other black holes and consuming gas. The Milky Way's structure includes a central bulge of old stars, spiral arms rich in gas and young stars, and a halo of globular clusters. Our solar system resides in the Orion Arm, between the Perseus and Sagittarius arms. The galaxy's rotation curve, stars moving at constant speeds regardless of distance, revealed dark matter, an invisible substance making up 85% of the universe's mass. Beyond our galaxy, the local group spans 10 million light-years. It includes Andromeda, M31, approaching us at 110 km/h and destined to collide in 4.5 billion years. Triangulum, M33, the third largest member, hosts star-forming regions 1,500 light-years across. Dwarf galaxies like the Large and Small Magellanic Clouds orbit the Milky Way, their gravity distorting our galaxy's disk. The local group is part of the Virgo supercluster, containing 100 galaxy groups and clusters. Virgo cluster itself, 54 million light-years away, houses 1,300 galaxies, including the giant elliptical M87. Its jet, powered by a 6.5 billion solar mass black hole, emits radiation detectable across the electromagnetic spectrum. On larger scales, galaxies form filaments and sheets separated by cosmic voids. The Sloan Digital Sky Survey mapped these cosmic webs, revealing structures like the Great Wall, 520 million light-years long. Yet the universe's expansion, driven by dark energy, stretches these filaments, accelerating galaxies apart. As we peer deeper, galaxies become time capsules. Light from GNZ11, 13.4 billion light-years away, shows the universe as it was 400 million years after the Big Bang. Each galaxy is a testament to cosmic evolution, a dance of gravity, dark matter, and time that shapes the universe's grand architecture. The expanding universe and cosmic origins. In 1929, Edwin Hubble observed that galaxies recede from us at speeds proportional to their distance. This relationship, Hubble's law, proved the universe is expanding. The Hubble constant, measured as 70 kilometers per megaparsec, quantifies this expansion, implying the universe began 13.8 billion years ago. The Big Bang theory describes this origin. Initially, all matter and energy occupied a singularity, a point of infinite density. In the first 10 to 32 seconds, inflation expanded the universe by 10 to 26 times, smoothing irregularities. As it cooled, fundamental forces separated: gravity, electromagnetism, and the strong and weak nuclear forces. By 1 microsecond, quarks combined into protons and neutrons. Within 3 minutes, nucleosynthesis produced hydrogen, 75%, helium, 25%, and trace lithium. For 380,000 years, the universe remained opaque, a plasma of nuclei and electrons. Then, recombination occurred. Electrons bonded to nuclei, forming neutral atoms. Photons decoupled, traveling freely as the cosmic microwave background, CMB. Discovered in 1965, the CMB is a snapshot of the infant universe. Its temperature, 2.725 K above absolute zero, varies by just 0.0003 K. These fluctuations, mapped by satellites like COBE, WMAP, and Planck, seeded cosmic structures. Denser regions collapsed under gravity, forming the first stars after 100 million years. These population 3 stars, massive and short-lived, forged heavier elements via fusion. Their deaths as supernovae enriched space with carbon, oxygen, and iron. Subsequent generations of stars formed in molecular clouds, giving rise to galaxies like the Milky Way. Dark energy, discovered in 1998, drives the universe's accelerated expansion. It makes up 68% of the cosmos, yet its nature remains unknown. Dark matter, 27%, interacts only gravitationally, forming halos around galaxies. Ordinary matter, stars, planets, us, constitutes just 5%. The universe's fate hinges on dark energy. If it remains constant, expansion will continue indefinitely, leading to the Big Freeze. If it strengthens, the Big Rip could tear apart galaxies, stars, and atoms. Alternatively, a cyclic model suggests contraction into a big crunch, followed by rebirth. Each discovery deepens the mystery. The CMB's uniformity hints at cosmic inflation. Galaxy rotations reveal dark matter. Supernova expose dark energy. Together, they paint a universe born from simplicity, evolving into complexity, a story written in light, gravity, and time. The search for extraterrestrial life and the future of space exploration. Life on Earth thrives in extremes: Antarctic microbes at 20° Maying, tube worms near hydrothermal vents at 121° Mayings, tardigrades surviving vacuum and radiation. This resilience expands the habitable zone beyond traditional definitions. Europa's subsurface ocean, heated by tidal forces, could harbor life. Enceladus's plumes contain organic molecules. Mars's ancient river deltas may preserve microbial fossils. Exoplanets, planets orbiting other stars, number over 5,000 confirmed. The TRAPPIST-1 system, 40 light-years away, hosts 7 Earth-sized planets, 3 in the habitable zone. Proxima Centauri b, orbiting our nearest star, receives similar energy to Earth. Telescopes like TESS and Kepler reveal diverse worlds, lava planets, gas dwarfs, and super-Earths. The James Webb Space Telescope, JWST, launched in 2021, analyzes exoplanet atmospheres. It detected water vapor on WASP-96b and carbon dioxide on WASP-39b. Future missions, like the Habitable Worlds Observatory, will search for oxygen and methane, potential biosignatures. The Search for Extraterrestrial Intelligence, SETI, scans for technosignatures, radio signals, laser pulses, or Dyson spheres. Projects like Breakthrough Listen target 1 million stars using radio telescopes. Yet silence persists, prompting the Fermi paradox. Where is everybody? Solutions range from the rarity of life to self-destruction of civilizations. Humanity's future in space unfolds across 3 horizons. Near-term, 2030s, Lunar Gateway, a space station orbiting the Moon, supports Artemis missions to establish a sustainable presence. Mars rovers like Perseverance collect samples for return, testing technologies for human landings. Mid-term, 2040s, 50s, crewed Mars missions face challenges, radiation exposure, microgravity effects, and 6-month journeys. Solutions include nuclear propulsion, cutting transit to 3 to 4 months, and regolith habitats shielding from radiation. Asteroid mining could provide water and metals, enabling in-situ resource utilization. Long-term, centuries ahead, interstellar probes like Breakthrough Starshot aim to reach Alpha Centauri in 20 years using light sails powered by ground-based lasers. Terraforming Mars, releasing CO2 from polar caps to thicken the atmosphere, could raise temperatures and create liquid water oceans, though ethical and technical hurdles remain. Space exploration also addresses existential risks. Lunar bases could back up Earth's biodiversity. Asteroid deflection systems like NASA's DART mission protect against impacts. Ultimately, space offers a path to transcend our planetary cradle, a vision echoed by Carl Sagan. The cosmos is within us. We are made of star stuff. As JWST peers into the universe's dawn and rovers traverse alien soils, we stand at a crossroads. Each discovery fuels the next question. Each horizon unveils new mysteries. The cosmos beckons, not with answers, but with the promise of journey. What lies beyond the next star? The greatest adventure has only just begun. Cosmic enigmas, dark matter, dark energy, and the universe's hidden framework. The universe's visible matter, stars, galaxies, gas, accounts for merely 5% of its total mass energy content. The remaining 95% consists of 2 enigmatic entities: dark matter, 27%, and dark energy, 68%. These invisible forces shape the cosmos, yet their nature remains one of science's greatest mysteries. Dark matter was first inferred in 1933 by Fritz Zwicky, who observed that galaxies in the Coma cluster move too rapidly to be held together by visible gravity alone. Decades later, Vera Rubin's studies of galactic rotation curves confirmed that stars orbit at near-constant speeds, defying Newtonian physics unless an unseen mass provided gravitational glue. Dark matter does not emit, absorb, or reflect light, revealing itself only through gravitational effects. It forms vast halos around galaxies, bending light via gravitational lensing, a phenomenon used to map its distribution. Leading candidates for dark matter include WIMPs, weakly interacting massive particles, and axions. WIMPs, hypothetical particles 100 times heavier than protons, would interact only via gravity and the weak nuclear force. Experiments like the Large Underground Xenon, LUX, detector search for WIMP collisions with atomic nuclei, while the European Organization for Nuclear Research, CERN, attempts to produce them in particle accelerators. Axions, lighter particles proposed to solve quantum anomalies, could convert to photons in magnetic fields, as probed by experiments like ADMX. Dark energy, discovered in 1998 through observations of distant type Ia supernovae, drives the universe's accelerated expansion. These supernovae, serving as standard candles, appeared dimmer than expected, indicating they were farther away than a decelerating universe would allow. The implication was revolutionary. A repulsive force counteracts gravity on cosmic scales. Dark energy's density remains constant as space expands, causing galaxies to recede ever faster. Theoretical explanations include Einstein's cosmological constant, a vacuum energy inherent to space itself, and quintessence, a dynamic energy field. If dark energy strengthens over time, it could tear apart galaxies, stars, and atoms in a big rip. Conversely, if it weakens, gravity might eventually halt expansion, leading to collapse. Current data from the Planck satellite and dark energy survey favor the cosmological constant, but its origin remains elusive. The interplay between dark matter and dark energy defines cosmic evolution. Dark matter's gravity pulls matter into filaments, seeding galaxies, while dark energy stretches these structures apart. Simulations like the Millennium Project model this cosmic tug-of-war, reproducing the universe's web-like architecture. Yet without understanding their fundamental nature, our cosmological model remains incomplete. As telescopes probe deeper and particle detectors grow more sensitive, humanity edges closer to unveiling these shadows. Each discovery reshapes our cosmic narrative, revealing a universe far stranger than imagined, governed by forces we cannot see, but whose influence is written across the heavens. The multiverse hypothesis, beyond our cosmic horizon. What lies beyond the observable universe? The concept of a multiverse. A collection of multiple universes emerges from several theoretical frameworks, challenging the notion of our cosmos as a singular, unique entity. While speculative, these ideas offer profound implications for reality itself. The Macaternal inflation model, rooted in cosmic inflation theory, suggests that our universe is one bubble in a vast inflating multiverse. After the Big Bang, inflation ended in our region, allowing matter and energy to form. Elsewhere, inflation continues eternally, spawning new bubble universes with potentially different physical laws. These universes would be causally disconnected, making direct observation impossible. String theory proposes another multiverse scenario. It posits that fundamental particles are vibrations of one-dimensional strings in 10 or 11-dimensional space-time. The theory allows for 10 to 500 possible vacuum states, each corresponding to a universe with unique constants, e.g. gravity strength, particle masses. Our universe's fine-tuned parameters, permitting stars, planets, and life, might be a statistical accident within this landscape. The many worlds interpretation of quantum mechanics suggests that every quantum measurement splits reality into parallel branches. For example, Schrödinger's cat exists in a superposition of alive and dead states until observed. In many worlds, both outcomes occur in separate, non-communicating universes. While controversial, this interpretation avoids quantum collapse and is mathematically consistent. Evidence for the multiverse remains indirect. Thus, cosmic microwave background, CM, shows anomalies like the CMB cold spot, a large, unusually cool region that could be a cosmic bruise from a colliding bubble universe. Gravitational waves from inflation, if detected, might reveal signatures of other universes. However, critics argue the multiverse is untestable, blurring the line between physics and metaphysics. Philosophically, the multiverse reshapes concepts of uniqueness and purpose. If infinite universes exist, every possible outcome, every life, every civilization may manifest somewhere. Yet this raises the measure problem: how to calculate probabilities in an infinite ensemble. Resolving this could redefine cosmology and our place in existence. As we stand on the shores of the known, the multiverse beckons like a distant shore, a realm where physics, philosophy, and imagination converge. Whether it remains a theoretical construct or becomes an observable reality, it underscores the universe's boundless capacity for surprise, humanity's cosmic evolution, from Earth to the stars. Humanity's journey into space is not merely exploration, it is an evolutionary leap. As Carl Sagan noted, "We are the way the cosmos knows itself." Now we stand poised to become an interstellar species, driven by necessity, curiosity, and the imperative to survive. Phase 1. Becoming a multi-planetary species, 2030-2100. The Moon and Mars are our first stepping stones. NASA's Artemis program aims to establish a sustainable lunar base by 2030, leveraging water ice in permanently shadowed craters for life support and rocket fuel. The Lunar Gateway, orbiting the Moon, will serve as a research hub and staging point for Mars missions. Mars colonization faces immense challenges. Radiation levels are 2.5 times Earth's due to its thin atmosphere and lack of magnetic field. Solutions include underground habitats or regolith-covered structures. Terraforming, altering Mars' climate to support life, remains theoretical. Releasing CO2 from polar caps could thicken the atmosphere, raising temperatures by 10 degrees Celsius over centuries. However, ethical questions arise. Do we have the right to reshape another world? Phase 2, the interstellar precursor, 2100-2200. Reaching nearby stars requires breakthroughs in propulsion. Nuclear fusion rockets, like the Daedalus project, could achieve 12% of light speed, cutting travel time to Alpha Centauri to 50 years. Antimatter propulsion, though energy-intensive, offers even greater speeds. Meanwhile, light sails, propelled by ground-based lasers, could send Gram-sized probes to Proxima Centauri in 20 years, as envisioned by Breakthrough Starshot. Phase 3, the Kardashev scale and beyond. Russian astrophysicist Nikolai Kardashev proposed a scale for civilizations based on energy harnessing. Type Y controls all planetary energy. Earth is 0.73. Type 2 harnesses a star's energy, e.g. Dyson spheres. Type 3 commands a galaxy's energy. Humanity could reach Type 1 by 2100. Type 2 might require asteroid mining and space-based solar power, capturing 100% of the sun's output. Type 3 civilizations, capable of manipulating space-time or creating wormholes, remain millennia away. Biological and cultural evolution. Space will reshape humanity itself. Genetic engineering could create radiation-resistant humans or adapt physiology to low gravity. Digital consciousness, uploading minds to machines, might enable interstellar travel without biological constraints. Culturally, spacefaring societies may develop new ethics, governance models, and art forms reflecting a cosmic identity. The ethical imperative. Expansion carries responsibilities. The COW, planetary protection policy, prevents contaminating other worlds with Earth life, preserving potential alien ecosystems. This outer space. Treaty of 1967 designates space as the province of all mankind, prohibiting weapons of mass destruction in orbit. As we venture farther, these frameworks must evolve to address asteroid mining, terraforming, and contact with extraterrestrial life. Epilogue, the unending horizon. As we gaze into the abyss of space, we confront not only the universe's mysteries but our own. Each discovery, from the quantum foam to the cosmic web, reveals a reality more intricate, more beautiful, and more humbling than we imagined. Dark matter and dark energy remind us that most of existence remains invisible. The multiverse challenges our definition of reality, and the prospect of becoming an interstellar species forces us to ask, what does it mean to be human in a cosmos of infinite possibilities? The journey ahead is fraught with peril, radiation, resource scarcity, existential threats. Yet it is also illuminated by hope, for knowledge, for survival, for connection. Perhaps the greatest lesson of space exploration is that we are both insignificant and precious, a fleeting spark of consciousness in an eternal void, yet capable of comprehending the stars. As Voyager 1 carries its golden record into interstellar space, a message in a bottle from humanity, we continue to reach outward. The answers we seek may lie in the next galaxy, the next dimension, or within ourselves. For now, the horizon beckons, not as an end, but as a beginning. The cosmos awaits, and our story has only just begun.